We're in Chapter 2, Mathletes, and we're discussing quadratic functions in this one. So this is 2.1, and we'll probably do 2.1 and then 2.2. And so 2.2 is actually polynomial functions, so we'll dive a little deeper into polynomial functions. These are some polynomial functions that we've studied actually. Well, today we're studying quadratic functions, or the squaring function, right? But we've studied these two before, right? Linear function, y equals mx plus b. Here you see ax plus b instead, so a is just the slope in this case, but it's a constant, right? So they're just using a instead of m, but this is a linear function. We know it's a diagonal straight line. We have a constant function, which is a horizontal straight line, and that's f of x equals a constant. So we've learned about these a lot, and today we're going to take a deep dive into the squaring function. Okay, just to show you on our handout what these look like, and again we've spent a lot of time talking about constant and the identity or linear function, and so we know a lot about those. And today we're going to key in on quadratic or the square function. Okay, and you can see that the graph of it is a parabola. You can see that the domain is negative infinity to infinity. It goes left forever and right forever. No matter what kind of parabola it is, no matter if it's in the family of quadratics, it'll have that domain. The range is a little different though, because since it's a parabola, it does have a low point, right? And so it doesn't go down forever. If it's an upward facing parabola, it would have some type of left or bottom endpoint, and then it would go up forever, right? If it's an upside down parabola, then it's going to go down forever, but it's going to have a top endpoint, right? Or in the right, if you put an interval notation, it'll actually have an endpoint there. Okay. Now, one thing I want to point out, we just talked about inverse functions last time, and this says that there's an inverse function, but remember, a quadratic or a parabola would not pass the horizontal line test because it would cross twice here, right? And we know that that functions that don't pass the horizontal line test don't have an inverse. And so this is a little bit of a stretch here to say this. The square root of x, remember, is this function. Looks a little something like that. So it is half a parabola on its side, like I've told you before. So it's really the inverse of just this part of it, right? It's not the inverse of the whole thing. Like if you erase this one side, if you erase the left side, the right side would pass the horizontal line test, right? It would just cross once. So that would be the inverse, but it's a little bit of a stretch. And you could see like it is reflected across the line y equals x, so that would work. But again, it's half of a parabola, not the whole parabola. So to me, I think I wouldn't. Yeah, I think this is a little bit misleading to say that that it has an inverse function. So let's remember that that's not exactly the case. All right. All right, so let's look at polynomial functions just for a second. So this is the form of a polynomial function, okay? So you can see that you have all these a sub n minus 1, dot, 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 right? So they continue a sub n minus 2, a sub n minus 3, then you get a squared, a to the first, a to the 0. Those are all your coefficients, okay? So a sub n, those are called coefficients. And they're basically just the constants that are in front of the variables, right? So those are our coefficients. And then you can see you have like n minus 1, and then dot to dot means you go n minus 2, n minus 3, n minus 4, all the way to get to 2, 1, this invisible 1 here, and then you get x to the 0 power, right? And so, and remember, x to the 0 power is 1, so that's why you don't see an x here, because it's x to the 0, so it's invisible. But that's when you just have a constant, right? Because you don't see the x there. And anyway, those these exponents here, those are the highest exponent, which is n, is called the degree of a polynomial. Okay. So what you would do is you would say this is a polynomial of degree blank, so degree n. And so it could be like a 4th degree polynomial or a 3rd degree polynomial or a 10th degree polynomial, et cetera, et cetera. And so a quadratic is a 2nd degree polynomial, and a linear is a 1st degree polynomial, and so forth. Okay, and so we've dealt with polynomials actually already, but basically polynomials can have a as high of a degree as you can go. So here are examples of quadratic functions, right? So you can see all of these are quadratics, okay? All of them have this degree of 2, right? X is raised to the 2nd power, right? In all of these. Even this last one, it looks like we don't see an x squared, but if we were to FOIL this out, it would turn into a quadratic, right? It would be x squared, and then we would get 1x minus 2x minus 2 if we were to FOIL this out, and that would turn into x squared minus x minus 2. And so you can see that it does turn out to be a quadratic and a degree 2 polynomial. Okay. And so anyway, just to show you that they come in all different formats, this is actually called standard form. And the book uses this as standard form. I've always heard this as vertex form. And I think the book uses those interchangeably, but standard form to me is this, where you have ax plus b, a squared, x squared plus bx plus c. And then this is kind of like a little bit in standard form. It's kind of a variation of standard form. Same with this. And then this, sometimes this is called like a roots form or zeros form, but it's or factored form, maybe is the best way to put it, or the most common way to put it. Okay. All right. And so those are some different forms of quadratics. So they can kind of come in different shapes and sizes in terms of the way the function looks. But the graph will be a parabola, right? And it'll be either facing up or facing down, but it'll be a parabola. It also might be shifted, right? Like a translation up, down, left, right, or it might be stretched vertically or horizontally, or shrink. It might be a shrink vertical or horizontal shrink. And so they can, again, come in different kind of shapes and sizes on the graph version as well, but they'll all be some version of a parabola, like a U-shaped curve facing up or facing down. And finally, you can see here's, like I said, what I consider to be standard form. And this is the book. The book doesn't say standard form here, but this is the definition of a quadratic function. So where you have these coefficients a, b, and c, right? So a is called the leading coefficient, all right? So this is the leading coefficient is a. And that's one that we look at a lot to tell us about the graph. It tells us whether the graph is facing up or down. If a is positive, it's facing up. If a is negative, it's facing down. We'll talk a little bit more about that. But yeah, that's an important one to look at. C is your constant. That's going to be your y-intercept. So just like y equals mx plus b, you can just see b and that's your y-intercept. The same thing if you have it in standard form for a quadratic, you can look at c and that tells you the y-intercept. Whatever the constant is in a polynomial, any polynomial, that's the y-intercept. Because if you plugged in 0 for x, this will go away, this will go away, and all you'd be left with is the c, right? So remember, that's how we find that y-intercept, is we plug 0 in for x. And so anyway, so that's why c is the y-intercept, okay? All right, now notice how they say a is not 0, because if a was 0, then that would go away and you just have a linear function, right? So a always has to be a number that's not 0. B and c can be 0, but for it to be a quadratic, you have to have a value there for a. Even if it's a 1 and it's invisible, you're still going to have a value there that's not 0.